Hello again, everyone. Good afternoon. We're going to go ahead and get started. My name's Allie. I'm with the CAE team. I'm just filling in for Josh since he couldn't be here today. So thank you for joining us. Our first speaker today is Dr. Kun Sun. I hope I said that right. He is from George Mason University, and he'll be speaking with us about the security patch identification on open source software. So I'm going to hand it over to him.
Okay, thank you, Ali, for your introduction. And also thank CAE give us this opportunity to talk about one of our work on software security. So here I first give some brief introduction about our center. So our Center for Secure Information Systems, CSIS, was founded in 1990 as the first academic center in information security at US University. So we are got both this as a center for academic excellency in information assurance for education and research. So for our center's mission, our focus on this doing this multidisciplinary research. So we work on a wide range of cybersecurity problems, and we have been collaborated with top researchers from different universities, from industry, and also our government partners. So we also do a lot of some of this transfer this work of our technical solutions to commercial products. And currently, our center has 5 faculties, and also we have 24 PhD students and 6 master students. So here I list some of our current key research area. So including this marine target defense or the cyber deception, how to just protect our system by moving this moving the IP address or memory layout offsite. And also another one is a network attack analysis, and also for the VR, AR security, virtualization, and also cyber situation awareness and cybersecurity analytics and automation. We have one NSF IUCRC center working on this cybersecurity analytics and automation. So for today's, I will introduce some of our work on software security, and we also work on trusted computing and AI or machine learning security, cloud container security. Okay, the outline for today's talk. So first, I will give some motivation for our research and give some then some background about what is a patch, software patch, what is a security patch, and then I will talk about our work, how we collect security patch and net security patch into one data set, PatchDB, and we have just open source this database, and also then. Sorry. I will introduce 2 of our work. Just one is a sequential-based model, another one is a graph-based model to identify security patch. The idea is if given large number of software patch, we want to know, okay, if some of them are security patch, and also do we need, as admin people, do we need to just take some actions? And finally, I will provide some discussion and conclusion. So for the open source software now is changing our daily life, right? Being used everywhere. And because we have this powerful community, so everyone can contribute their code and share with other people. So we don't need to write the code from scratch. We can just borrow some code from those open source software repository. So it's just improve the efficiency. So now the problem is, okay, for this open source software, like other software, it contains vulnerabilities. And those vulnerabilities will be propagating from those upstream software to the downstream. And there's some report size, okay. Currently, like those 97 software, they may contain open source elements. And 81 of those open source components may contain at least one vulnerability. And 49 contain at least one high risk vulnerability. So this is how to fix those vulnerability in open source software is a critical problem. And here, when vulnerability in OSS being identified, it may be reported to some vulnerability database like the NVD or CVE, right? So, and then this will be can be notified by the admin, and also around same time, attacker can just monitoring those database. They can see, oh, if there's some new vulnerability being reported, and they will see, because the existence of the end-day attack. End-day attack means after one vulnerability is being reported, and also some patch may be provided, but this vulnerability will not be immediately being fixed, right? For example, in this GitLab, this DDoS attack, right? One CVE was reported in April 2021. And after 7 months, actually, attacker launched this DDoS attack, actually compromised over 30,000 GitLab servers. And this means between these 7 months, still more than 30,000 GitLab server has not fixed this already identified vulnerability. So we call this, this is one example of an end-day attack. So to solve this problem, the best practice is to timely patch the software. But here, there's two challenges. One challenge is, okay, now daily reported a large number of various patches, including this security patch and the non-security patch. And how do we know which security patch? So on the other side, also not all those security patch will be reported. So some software vendors, they may just silently or secretly fix some vulnerability without report this vulnerability to the CVE or NVD. So for those admin people, they see, okay, there's some new patches, but it's not reported as security patch. They may delay the upgrading of the system. So our work focus on this security patch identification. So the goal is we can just identify security patch from those new released patches. And then we can help admin people to prioritize their patching work. So now some background. What is patch? What is security patch? What it looks like? What's the definition? So in general, a patch could be is a set of changes between two versions of source code. It could be one simple commit, like this figure shows, right? Or it could be a collection of commit, multiple commits, or it could be just an update package, right? We can also call this like a patch. So for our study, we will focus on this commit, a single git commit. We consider this a simple git commit as a patch. So we see here in this patch, there's a subject, right? So it's like a commit message. And also it will tell you what software and which file being modified, okay? The plus means actually this is the new code in the new version. So if there's a minus, means that's the deleted code in the previous version. And here, we define this security patch, okay? So if it fixed a vulnerability belonging to any of these CWE tabs, right? CWE, it just give you more than 100 different type of vulnerabilities. So if we see there's one vulnerability belongs to this CWE and there's a patch to fix this one, then we consider this as a security patch. And there's some challenges here. So why we need to clarify this, what is security patch? So because CVE actually, or CWE, those assignment is quite subjective. It depends on those admin people or maintainers, right, of this different CNA, it's the CVE numbering authority. They can give you the different this category for those vulnerabilities. And actually, or even for CVE or CWE, they will change their classification from time to time. And also for those, there's some argument always like, okay, if you don't find a POC proof of concept, you cannot just prove this vulnerability will be really can be triggered. They may not consider it like a real vulnerability, right? Some people just hold those opinion. That's reasonable. But on the other side, if you don't, in our work, we just consider, okay, if there is a vulnerability and there's soft code to fix this vulnerability, then we consider it like a security patch, no matter they can provide a POC or not. So then the next question is, can we fundamentally distinguish security patch from non-security patch, right? We do some preliminary analysis, compare these two categories. We can see here for security patch, usually it will add some sanity checks, like if this pointer is a null. And also it will use the typical specific API calls like memory malloc, and also like a lock related API. And also another thing is the patch size. Usually for security patch, their size is smaller than those non-security patch. So this figure on the left just shows actually for the security patch SP, actually for this one, the relatively the patch size is smaller than those non-security patch. And another thing is, so because there's already a lot of work, they can identify this vulnerability. So that's also why we have the confidence from the beginning, say, okay, we can also distinguish the security patch from the non-security patch, right? Because the security patch is trying to fix a vulnerability as the pre-patch version. So when we start working on this project, we just see, okay, if there existing some security patch database, we found some, but they have very just a limited size, just 1,000 security patch. And also they only focus on specific one or two different security repositories. And also they have specific patch tabs. In other words, there's lack of really general security patch database to cover, to provide a large number of those patches. And also on the other side, we also need a database for the non-security patch, right? We want to make sure for those non-security patch database really does not contain security patch. So first we can just from MAD, this database, we can collect those of around 4,000 security patch related to C or C++. So for our work, we focus on C and C++ language. So our the whole process to construct our database is contained like three parts. One is we first crawl this from the MAD database, right? Get this 4,000 patch, and then we do through the second step, we do one augmentation. We try to find more security patch or a non-security patch from the GitHub commits, and then we can collect this wild-based patch. And then third step, we do some oversampling. We can create a more synthetic patches. So for the second step, after we collect more than 4,000 security patch from NVD, we do this data augmentation. So the main idea is, okay, we observe around 8% of the GitHub commit, actually they are security patch, okay? But they may not be given a CVE ID. In other words, it may not be reported to CVE. So from those GitHub commit, we can get more security patch. And then how to do it more efficiently? We first, okay, collect this 4,000 security patch from NVD. And then we just compare using one nearest neighbor algorithm. We find a group of candidates which looks more similar or more likely to be security patch, okay? And then we found those candidates, we verify them manually. We use 2 students and 1 postdoc. They do cross-checking, see manually check if they are real security patch or non-security patch. So if they are security patch, we add them into the original security patch, and the non-security patch, we will go to the non-security patch database. So then we will repeat this step again, okay, using this enlarged security patch to find more candidates, and then do this candidate this manually screening. So after like 5-6 round of those manually screening, so we can construct a large data set which contained more than 12,000 security patch, and also more than 20,000 non-security patch. So here, this is the idea for how we select those candidates, right? So is try to find the most promising candidates, which could be a security patch. So here, this is in the wild, we found already identified those red dot already labeled security patch. And then we use this nearest link search. We find, okay, who really looks like more likely to be a security patch, and then we do manually verification. So we compare our nearest link search algorithm with the existing other solutions. For example, what if we just do a brute force? We just give me a number of this Git commit. We just screen it. We can identify like 8% security patch. Or we can just build a machine learning model and then use that to identify some more security patch. So the percentage using this pseudo labeling is 13%. Or we can use multiple this machine learning classifier, right? They get a consensus, okay, which is more likely to be the security patch. For this, we call it uncertainty-based labeling. This can achieve 12%. And for our solution, we can achieve around 29, around 30%. So it means from those candidates, 29% of those candidates will be security patch. So in the end, we got 12K security patch, 26K non-security patch. And from those database include more than 300 software repositories. And also we further just divide those patch based on, okay, what's their patch pattern? Do they add or change some bound checking or null checking? Okay, based on their actions. So we also do some breakdown analysis on those numbers. How many numbers fall into each types? So we will see here in this type 8, add or change function calls. Actually, in this wild base, we found more of this type of security patch in our data set. Okay, so now after we got this large size of data size. So we can use deep learning. This is a now powerful deep learning technique to help us to identify security patch. So the first attempt is we using this RNN, okay? So which can deal with natural language processing task very well. So we call it a sequential model scheme. So we consider both the commit message and also the source code revision as the input to our model. And then we build this sequential and context-sensitive model. So this is as the input. For the input contain two parts. One is the commit message. It includes the subject and also the description. This is also provided by the committer, right, when they submit this commit message. And also the second part is code revision. Okay, this is about what being changed. We can see here in this example, this minus marked minus means these 4 lines will be deleted, and this plus means this is a new line will be added. And usually for one commit, it will include 3 lines of this context line of code, right? This is will not be changed, but it will include 3 lines of this before and after this change. And also for one group of these minus and plus, we also call them like chunks. So this figure shows the architecture of this PatchRNN. It contains 2 parts, right? One is for this given one patch, we got this the diff code. This is on the code revision, and also the commit message. And for the commit message, we will process those like using the natural language processing mechanism and go through this text RNN. We can generate this messaging vector. Right here, this is one just focus on this text RNN. Right? We do this cleanup, tokenization, and stemming, and then we can after getting embedding, and we have text RNN. This is how we process this commit message. And for the code revision, we got 2 versions of this the source code. One is a vulnerable code, the other one is a patched code. This is both derived from the diff code. And then we do this tokenization on both this piece of code. And then we use this twin RNN, okay, on this patched code and vulnerable code. And then here we can just connect, like have a fully connected network to connect both these code vectors from this and message vectors from the commit message and the diff code. Then we do this prediction. So the performance of this PatchRNN looks pretty good. So accuracy could be above 83%. And also it can pre-process one patch in 4.4 seconds. And given one patch, it can make the prediction in 1.2 seconds. So here because for the PatchRNN using both this commit message and the code revision, we just study, okay, which one contribute the most? Actually, our study discovered that the commit message actually provide most of the contribution. Right? So actually, in this study, if we remove this commit message, actually the accuracy will drop to around 50 or 60. This is not good. Then we ask ourselves, can we do better if we don't have this commit message? In other words, only based on code revision, this message can we also achieve a good accuracy? This is a real assumption, right? For some of this code, you can just give me a two version of the software, source code, but there's no commit message attached. Then I still can tell you, okay, if this between these two versions, is there any security patch? So next, we build up this graph-based scheme, which based on the graph neural network. This one we just compared to the previous work, we just see, okay, we need to contain more of this long span dependency, like the control dependency, data dependency, and also the abstract syntax tree. In other words, we contain more code semantics in our study, so to improve the performance of our prediction model. So this figure give an overview of this our graph SPD. SPD means the security patch detection. So first, given one target patch, we can build one new data structure called PatchCPG. This contain those control dependency, data dependency, and AST. All those information will be included in this PatchCPG. And then we do this embedding, and for this embedding, this will be used as input to our PatchRNN, which is our detection model. Then we make the prediction. So this PatchRNN is a graph neural network-based solution. So the first part is, given a patch, we need to construct a program this CPG, right? This CPG include both the control dependency and the data dependency, those information. So the idea is, from the patch, we got this before version and after version. And since this only contained commit, we need to get all those related files to get the whole related functions. And from those functions, we can get this CPG as a code property graph. We can build this post-patch CPG and a pre-patched CPG. And then we merge these two CPG into one one graph. Okay, you can see here, this is like some code will be deleted. This for marked as red, and some new node will be introduced, marked as a green color. But we will merge all those changes in one graph. So we can see one example. So first, given a patch code, here we see there's a delete one line and just replace it with a more secure version of the string copy using a string L copy. And from this patch, we can recover the pre-patch function and the post-patch function, what it look like. And from those functions, we can build this pre-patched CPG code property graph. And this is for the post-patch CPG. Okay, this looks different. So next, we mark those nodes with three different types. So it could be each node could belong to the deleted node or newly added node, or it could be a text node, means it will not be changed. It will show up in both the pre-patch CPG and post-patch CPG. So we can mark those nodes with different types. And similarly, we can mark those edge with different type. Then we can merge these two CPG into one patch CPG. We call it a patch CPG. We merge those identical node and retain the changed code. So after merge these two CPG, we got this red means the deleted, and also the green means that's newly added. And also for the edge, right? The edge will be marked as the start ID, end ID, and type, and their version. So after we generate this patch CPG, one challenge we faced is the size is too big, is very large, right? So, and also not all those context information will be useful. So we propose a slicing using the slicing technique to prune the graph, make it smaller, and also only just get the most relevant information, the code. And so we provide different options. Actually, we can consider those including the context node within certain hubs or distance from those deleted or added node. We try different options. Our results just tell us, okay, if we only consider those context nodes directly connected to those deleted or added node, the performance is good. So that's we just take these settings. So for those embeddings, for the node embedding, we use a 5-dimensional binary vector. We use a 2-bit to show if it's a pre or post patch, belongs to which patch. And also we use a 3-bit, just one hot vector to show, okay, it belongs to control dependency graph or data dependency graph or the AST. So for example, for one this edge embedding, 11010 means this edge is a context edge. This 11 is context, and also this 1 means it's a data dependency. And also for the node, for node embedding, we define this 20-dimensional features. Those features are vulnerability relevant features, including those code snippet metadata or control flow features, operator features, or API features, including different categories. So after we develop our this GraphSPD, we compare it with our previous work, this TwinRNN, right? So when we just only use this code revision in the TwinRNN, we see here this accuracy is 69%, but for our GraphSPD, also only solely rely on this code revision, we can achieve like 80%. And also for F1 score or precision or other metrics are also better. And also we compare our GraphSPD with other vulnerability detection method. So besides our our solutions, TwinRNN or GraphSPD, we cannot find other detection model directly working on the patch. So that's why we compare with our vulnerability detection method. So we just see, okay, how well they can identify this vulnerability before the patch and also after the patch, right? So if they are doing a good work, they should identify vulnerability in the pre-version, and also they should not detect those patch after it is being fixed in the post-patch. So the result is we can just find more security patch than all those previous existing works. And we do some case study. Is we use our this GraphSPD on this Nginx, this web server. So we work on this different version of this Nginx. We just see, okay, how many total commits between these two versions of the software. and how many of these are valid commits. And we see how many of this, we can detect how many of this security patch, and we manually confirm really they are really a security patch. And then this, we report this our precision, okay? How this detected, this is reported in overall among these 4 versions, we using our tools, it reported like 27 security patch. Those are not reported to the CVE. Okay, CVE originally they only report 8. Those 27 now included has not been reported to the CVE. And among these 27, we manually verify, okay, 21 is the real security patch. Okay, so there's a precision is like 78%. And we also try our tools on other software like Zan and OpenSSL or ImageMagick. And also we can successfully detect a number of those security patch. For those security patch is not just, has not been reported to the CVE. So here we provide some further discussion among these 2 schemes, PatchRNN and GraphSPD. So for the PatchRNN, actually is just use this code as sequentials, right? And for Graph, from the name, it's based on the graph neural network. So they present code as graphs, and we have node and edge in this graph. And also this for PatchRNN, they only consider those sequence with limited context, right? With this 3 line above and 3 line below, those change the code. And for the GraphSPD, they consider more this context dependency because they include the data dependency and the control dependency, right? This could be some code far away from each other. And for the PatchRNN, use both the commit message and the source code. And for the GraphSPD, use mainly on the source code. And for performance running speed, PatchRNN running pretty faster, require low resources. And for GraphSPD, because they need to process the graphs, so it has a higher overhead. So for the future work, so for our current graph SPD, it mainly focus on the single function. So we will consider how to just extend it to cross function. When there's a vulnerability, they need to make change among multiple functions. How do we deal with those functions? Like we need to consider those co-graph. And also another thing we are now working on is how to do this automatic patch generation, right? So what we have done is the first step. We just say, okay, provide tools to help automatically identify or distinguish security patch from a given set of patches. But then to solve this problem, can we just automatically just generate some suggestions to patch those some vulnerabilities, right? This is like now we have this data set, we have this PatchDB data set. We not only have the vulnerable code, we also have this patched code. We know, okay, for a given side of this type of this vulnerability, what their patch or fix will look like. Is there any patterns, right? We try to just using some machine learning or deep learning to help us to automatically generate those patch. So later, when you give me one specific vulnerability, I can just automatically generate a number of patches for the developers to use. And another works is for the related to explainable AI. this is about for when we submit a paper to IEEE SMP, Security and Privacy. Actually, some reviewers just ask us, okay, why your solution can do better than those patent-based existing solution, right? Why we can do better. So, but this is related to this explainable AI. That's we have do some preliminary analysis, but we will look into more, like see, okay, why our deep learning or graph neural network based solution can find more security patch or vulnerabilities than those previous patent-based or the signature-based detection models. So conclusion, so for our work is focus on this patch management and how to help those admin people to identify a security patch and give them some guidance to help them prioritize their job on fixing a number of those given patches and to prevent or mitigate those end-day attacks. And our work shows actually security patch can be distinguished by some unique patterns and by represent the patch as sequence or graph. We developed two models which can just provide a good result on identify those security patch from those non-security patch. Okay, this is the references. So this PatchDB is published in DSN. So the PatchRNN is in Milcom, and the GraphSPD in next year's IEEE SMP. Okay, thank you. I think that's all. I'm ready to take any questions. I think we have like 50 minutes, right? So we can have like 8 minutes for questions.
Yes, if you have any questions, you can go ahead and unmute yourself. It looks like someone just asked a question in the chat. Did you investigate why some of those detected SPs were not actually confirmed?
Oh yes, we also look into those some why there's some false negative, right? Some actually they are not security patch, but why we just consider is that's one reason is for some of this security patch, they are really looks like this non-security patch. It's difficult to distinguish them, to tell them apart. That's there's still have some limitations. For example, if like you add a security checking, that's you could just add if checking one variable equals to certain value, like sanity checking. But also some non-security patch, they just add a new function. They also may add some of those statements. So in some cases, without consider other context information, it's difficult to distinguish those cases.
Thank you. Does anyone else have any other questions for Dr. Sun? Do you have any recommendation? Do you have any recommendations on tools for managing patches?
For managing patches, this usually we talk to some industry the admin people. Usually for different companies, they have their own patch management tools. There's not just like one thing they always are monitoring those CVE MAD. Okay, see what is reported there. If there's a high risk vulnerability being reported, they may give a high priority to fix it. And also, there's a lot of constraint, right, on what their services they are running. So sometimes they need to wait until the midnight, right, or the weekend, they can update the system. And only when there's some really bad, severe vulnerability is going viral, actually they need to take immediately actions. But usually they will have their tools to prioritize, okay, for number of patch, even the security patch, how they fix them one by one or in bunch.
Thank you very much. Any other questions for Dr. Sun? Okay, if there's no other questions, I just want to thank Dr. Kun Sun for speaking with us today and taking time out of his schedule to be here. If you have any other questions, you can see Dr. Sun's contact information on the screen. And at 2 p.m., we will have Massimiliano Albanese from George Mason University speaking to us. And I will give the title of his talk once we start it back at 2. So thank you again, Dr. Sun. I really appreciate it.
Thank you, Patty. Thank you, everyone.
So